Hello, good evening, everyone. Thanks for staying that late. I'm Maciej. I'm software engineer here at Box, mostly focused on iOS.
Hello, I'm Magda. I'm senior software engineer working on Android application. And I will be back for the second part of this presentation.
Okay, and today we'll be talking about composable architecture and how we ended up using it at Box. Okay, so we'll give you some background, we'll talk about the architecture itself, and then we'll focus about how we implemented it here and how it looked from like 3-year perspective. Okay, so just for context, Box has two code bases, one for Android, second one for iOS and visionOS. And these code bases evolved for over 10 years. Actually, we can find some comments back to 2013. And they evolve completely independently, meaning that there's no unification between platforms. So if some iOS folk had a problem, he couldn't really consult that with Android one. The only common part was network requests, and that also this was usually the same. Okay, so also it evolved creating mix of everything. So it was mostly untested code, tightly coupled code, untestable code. Things changed in 2020 when we defined like the data access layer architecture, which was the first one which was common between platforms. You are still separate code bases, but the concepts are the same. So it improved things a lot since actually the iOS and Android engineers started to talk, started to design things together. It was data layer. So nothing was present in for the layers above. And 2031, Box comes to Poland. Mobile team is created as the first one here. And we are to create some new features. And we realize, okay, there is no path forward. We don't know how to do this. We can find some MVVM. We can find some clear architecture. We can find whatever it was trendy at the time. So we decided, okay, no, we need to focus on this and solve this problem. We need to find out some common presentation layer, which for us had to have a few properties. First, we needed to share the same concept between platforms. It worked for data layer. We also wanted engineers to talk when designing the presentation layer. We wanted something which is simple to use, without much overhead, but still something that has like a clearly defined communication paths and responsibilities, so like the code stays consistent. Like Box code base is enormous, so there was no way we would rewrite everything. So we needed something that could be plugged into existing solutions, something that could work both with the new UI frameworks, like SwiftUI or Compose, and the old ones. We need something that will be allocating small components that could be tested and reused, since right now we are duplicating a lot of code. And last but not least, something testable. We write tons of tests here at Box, and we really like to write fast and stable unit tests, not the heavy, slow, flaky functional ones. So we decided that we need something that will allow us testing on this lower level of testing pyramid. So we are starting looking for Holy Grail. That was quite crazy times. So we've analyzed probably dozens of different architectures. We checked ones that companies like Uber, Spotify, or Airbnb uses. We try our own, design our own extensions to MVVM, but actually nothing really checked all the boxes. Well, nothing except one architecture, which is the composable architecture designed by Point3, like two folks mostly focused on Swift. So how many of you heard of it or used it? Okay, good, that's nice. Android folks probably are the minority, so we'll talk about it a little bit. So why we found that's probably the ultimate solution, or what is TCA at all? So according to authors, the composable architecture, or TCA, is a library for building applications in a consistent and understandable way with composition, testing, and ergonomics in mind. Well, that sounds really cool, doesn't really tell much, though. So let's do some quick course of TCA. So this is like unidirectional pattern, a little bit similar to Redux. So if any of you touched web programming at any point, some concepts might sound pretty familiar. So everything starts with a store, which is like the main component that is visible for the outside world. And it has everything to go from like the data service layer up to the UI. We have system view, which will render our data, like for iOS it will be SwiftUI or UIKit. The view needs something to render, right? And this something is a state. So state is a clearly defined entity. It's a lightweight entity, so on iOS it will be usually a structure enum. And it becomes the source of truth for the whole UI. This is observable, state is observable, meaning that the view will get all the updates that happen to state, to re-render stuff. And very important characteristic of the state is that it's immutable for everyone outside the store. So the view has no way to directly change the state, which would be a little bit boring if the state couldn't be changed at all. So all the changes are done through actions. So action is actually an event that can be sent to the store, and this event at the end can trigger some mutation. All these actions are clearly defined for the store. So this is like a predefined set, meaning there will be no surprises here, what's being sent. And then we have a main logic component here, reducer. And this is one that's responsible for mutating the state. This is actually a simple function that takes the old state, the current state, the action, and produces a new state, which then is published to view. And this all runs synchronously. So all the state updates happen synchronously, always from the UI thread, so it's like no data races here, and also improves testability a lot. But well, the world isn't synchronous at all. We need to make network requests, access databases. We definitely don't want to block UI thread for this. So this here introduces concept of side effect. So besides mutating the state, reducer can emit a side effect. And side effect is actually some asynchronous action that will happen sometime, will be run sometime by the store. This is actually a block of code, which is also asynchronous. This could do anything, like communicate with the lower layers, make network requests, access some data, or like start observing user location. So this means that side effect can also be like long-lasting, potentially to the lifetime of the store. And the only entity that can change the state is reducer, and there's no exceptions here, meaning side effect also cannot change the state. What it can do is to emit action that again will be handled by reducer, which in the end mutate the state. So this is pretty powerful and like complete, because a lot of Redux-based architectures have this state action reducer, but they miss the side effect part. So this is nice because it's really clearly defined, and defined in a way that is easily testable, but that was not enough for us to decide on it. So let's focus on what C means in TCA. So it's composable architecture, and by composition, I mean like breaking down larger features into smaller components that can be like tested independently, create their own domains, and then easily bring back together to form like our great feature, bigger feature. Okay, I will give you some example to better understand this. So let's assume we are creating a sign-up. So user creates account, they need to create a password. This password needs to fulfill some requirements. So we are focusing on this password feature first. So we create some state, right? This will be like what user input, the flag indicating if this input can create a valid password, and the error message if it's not valid. We have an action that will be executed when the input is changed. And we have some logic here. So we see that when the input is changed, we run some logic that checks whatever our requirements are for the password. We also see this return none means that there's no side effect here. Okay, and now we can create a view that works with this small feature. So it takes store of this feature and basically binds to the state and binds to the action, like the input and input changed. And if we have error message, it also will display it, right? Okay, so that is nice because we can create this small component, we can test it, like create unit and snapshot test just for it without really caring about the big sign-up. But in the end, we do care about big sign-up. So we have this sign-up feature, which has own state, own set of actions, own logic, own view, right? we want to bring this password input feature into it. And that's actually where the power of the composable architecture comes in. This can be all done in the reducer level, meaning we add the password to the sign-up feature, which is the state of this password feature. We add an action that will come from the child feature. And now we define that our reduce logic is not only our presentation logic, but also we need to run the password input feature reducer. And that expects different state, right? That expects password input state and password input action. But the way we define state and action means that we have those. So we do what is called scoping, meaning we are extracting part of the state, and we are like putting this small action into our big one. And the TCA does everything around it. So it makes sure everything is synchronized, everything is run. It's very similar in the view. So we put this password input view, and we need to pass the small store, so the store of password input feature. We have a store of sign-up feature, but again, we can just scope it to the small one. And this might sound okay. I can do that in whatever, MVVM or whatever. But when you look at it, we compose it on the reducer level. Reducer has nothing to do with the UI. This is pure Swift code. We could compile it to WebAssembly, for example, or whatever, which means also that we can unit test it. So we don't really need to create UI to test how our feature behaves. So yeah, this example was a simple one, but this could become much more complex. So we could have a collection of features. So when you have a list of items, each item can have its own, like reducer, which means that, for example, in the UI, you have a button in a cell. It's super straightforward, and all the logic that happens is defined in the reducer. We could actually define navigation into other features that way, and this is all done in reducer. We are not creating UI at all, which makes testing a breeze. Since we can test these small features like password input independently, we can test sign-up feature independently, we can test how they behave together. And if we want to test some UI, we can write snapshot tests. And these are also quite easy to create because the view just renders the state. So if you just prepare the state we want it to render, well, it will. Okay, so that was the basics of TCA. And because of all these features, we decided, okay, let's give it a try and see how it fits into our app. Okay, so iOS was easy one. Because 0.3 are obsessed with Swift. They are they're pushing Swift to its limits. So they provided Swift implementation, Swift composable architecture. And this is extremely well documented stuff. So if you try to look how to document your code, just look at their code and you will see how. And they have also a blog and video series which really describes this concept a lot. So in the end, we've analyzed this code, which was also written in a nice way, and decided to bring the library as it is, with the exception of navigation. 2021, they didn't really have support for navigation. They relied on SwiftUI. SwiftUI navigation, let's say, isn't perfect, and actually it fails when we need some complex state restoration, like multiple pushes, for example, which we needed. So we had to created our own, kind of recreate what SwiftUI should do. But yeah, that was iOS. Android was a little bit more tricky, but yeah, it's over to Magda.
Yeah, thank you. So on Android, introducing the composable architecture was much harder task, mainly because we don't have such a well-known, well-supported library for Kotlin as we have for iOS. At least we didn't have when we were searching for it. We found some ports, however, they were not acceptable for us to use in our production app because we didn't like their API. Also, we were not sure if those libraries will be maintained and how long will be maintained. At the same time, the most common architecture patterns are on Android, so MVVM or newer MVI, they have no composition concept at all. And we found the composition very powerful tool, and we really wanted to have that on iOS, on Android side as well. Also, the Swift composable implementation was quite simple, well documented. It was simple enough that even me as Android developer, I could understand more or less what's happening there. So what do you think? What could we do with this? We decided to create our own Kotlin version of the composable architecture from scratch. I mean, not entirely from scratch, because we have very good example in the Swift code from the point 3. Let's see how it works in Android world. So we have a store that is just a class implementing the store concept. Inside it, we have a state, and state is a regular Kotlin flow. Next to it, we have implementation of the UI logic in a reducer. And reducer, again, is just a class implementing reducible interface. Since state is just a flow, it can be collected by our UI. And UI, based on this state, can render or update view accordingly. It works both with the composable UI and with Android views. However, it looks much, much better with the declarative style of the composable UI. View can then send actions back to store, for example, upon some user interactions. And to make it all work nicely with Android architecture components and with their lifecycle, store is located inside a view model. And that gives us a couple of benefits. First of them is that store survives configuration changes. And second is that we can use view model coroutine context. We use it to make sure to close the store and all the pending effects whenever view model is destroyed. Such a view model with a store is typically created per screen or per feature, whatever fits best. And such a feature typically consists of some smaller features or some smaller UI elements that has their own logic, their own complexity. And this is where the decomposition is so powerful. Let's see that on the example. We have document scanning feature code here, the part of this code. The document scanning feature consists of 3 sub-features, 3 pages: scanning, editing, and reviewing. Each of these sub-features has its own logic in the reducer and also has its own composable UI. All of them compose together one greater document scanning feature. On the UI side, document scanning composable takes the store as a parameter. It can be taken from a view model, it can be passed from other composable, and it is scoped to the smaller store that works on some smaller state and smaller piece of actions. Here we scoped our store to work on scanning page state and only scanning related actions. This smaller scoped store is then passed to the scan page composable. It works very similar on the reducer side. We have document scanning reducer that has its own logic, but also is composed out of reducers of these smaller sub-features. Here we can see how we can add scan page reducer that works on the smaller scan page state and only scanning actions. After we changed how we write our UI code, we also could significantly change how we write our tests. Before, the only reliable way to test our presentation layer was with instrumented functional test. And maybe some of you know that instrumented test can be a real pain. They are expensive in terms of time, resources, maintenance. They like to be flaky. With this new architecture, we managed to test almost whole UI logic with just simple unit tests that are fast and easy to write, because we just test reducers that are simple Kotlin classes without any dependencies to Android. Upon that, we could introduce snapshot tests, and on Android we use Paparazzi library. It runs locally without need to have device or emulator. So those tests are pretty fast and also easy to write. And we're kind of game changer in our project because that was the first time we could cover with test our views, our visuals. On top of that, we have some component tests with Roboelectric. They are also run locally, are fast enough, and they cover some complex cases that cannot be covered with snapshot or unit tests. On top of that, we still have some functional tests for some special cases that cannot be covered with cheaper tests. However, we try to have those tests as few as possible. And now, 3 years passed since we introduced this architecture. After those 3 years, for sure we know all the pros of this architecture, but also we are aware that it has some problems. However, we are happy with that and we are still using it. All new features are created with the composable architecture. We also ported a few our core features like preview or browse to the composable architecture. What is more, we delivered those features and they work. We see a few benefits. One of them is common design on both platforms. So developers from Android and iOS can create design together, discuss implementation. We can copy good solutions from each other. We can solve problems together. The code looks similar, so me as Android developer, I can actually understand what's happening on iOS side because I'm looking for known patterns like state, reducer, actions, environment. So definitely it helped to promote collaboration inside our mobile teams. Another big benefit is that our presentation layer code is standardized, structurized. The state is clearly defined in one place. On Android, this is a data class. So looking at the state, we can easily guess what is the responsibility of this component, what is displayed. Very similarly with actions, all the actions are in one place. On Android, this is sealed class. So again, looking at this action, we know what is happening in this component. Analogically, all the external dependencies are clearly defined in the environment. Another huge benefit is the ability to write small components that are focused on one purpose and can be easily reused in many places in the app. They can be in straightforward way reused in other parts of the app that follow the composable architecture, but we are also able to integrate them with some legacy code without a big pain. Another huge win, and this is really a huge win for us because at Box we have very high testing requirements, is the testability. With the composable architecture, we managed to test almost whole presentation layer code with unit tests and snapshot tests. Both of them are fast to run and easy to write. It's also much easier to write presentation layer component tests, as it's very easy to provide test data, as it's just enough to mock or fake the dependencies grouped clearly in the environment. However, of course, this is not a silver bullet. We are aware that we have some problems with this architecture. First of them is learning curve. New developers that join our team must spend some time during onboarding to learn the concept of the composable architecture. And after that, they spend even more time to learn how to use it properly. One of the reasons could be that this architecture is not so well known in the mobile world, especially on Android side, and there is not so much learning resources, mainly tutorials from Point3, which are good, but again, mainly for iOS developers. It seems that these composing and scoping aspects are the least intuitive part of this architecture. Again, maybe because they do not exist in other common patterns like MVVM. Another problem that we see is something that is called massive reducer problem. Since this architecture actually promotes writing small focused components, it's also very easy to extend existing components. And that can lead to big reducers that are responsible for thousands of stuff. However, this is true also for like class or function, right? It's also easy to create giant class if we just add stuff there and never do refactors. However, it seems that extracting class or splitting a function is something that developers do very intuitively. However, extracting reducer is not so intuitive, and developers are kind of afraid of it. So this is something that we are constantly working on in our project. And finally, at the beginning of this journey, we were complaining that we have too much patterns in our code base. And now we have one more pattern, because it's, of course, not possible to refactor everything at once. However, we are very happy with the composable architecture, and we want to leave you with those key points. So the composable architecture is UI architecture pattern. It promotes composition, reusability, and this composition part is the differentiator of it amongst other mobile patterns. If you are iOS developer, you can try it right away with the point-free library. However, there is not well-known implementation on Android yet. Maybe we will open source our one day. The composable architecture definitely improved the quality of our presentation layer and increased testability. However, of course, it also has some problems, and we should be aware of it. Anyway, we recommend to try it if you have a chance. And now it's a time for your questions.
Okay, so the question was how do you convince QA team to write this other type of test? And actually the answer here is pretty easy, because the QA box works in a way that we have some people that do mostly manual tests, but all automated testing is on engineers. So it's on us. So it was our benefit that we don't really have to write those functional tests, which no one really likes, and just write the unit once. So yeah. So the question was if you use it with UIKit or SwiftUI, right? So it's mixed of both. So the new features, we try to use SwiftUI because it's similar to Android. It's much easier with SwiftUI and composables. Although well, SwiftUI doesn't really work for some cases, like collection views, which are really not performant with a large amount of data. And we also sometimes need to use like legacy components, so we have also integrations in UIKit. It can be done in both ways. It's much nicer in SwiftUI. The code is much concise, but still, because we just observe the state, it's perfectly doable with UIKit. So for navigation, we had our own solutions because we needed to support like box state restoration, which again is a custom one. So yeah. Although like Point3 recently for iOS introduced their own navigation library, probably worth trying. Honestly, we haven't tried it yet. They have one, something so may work better than SwiftUI one.
Could you please repeat the name of this library? This I didn't hear. React Core. Sorry, it's MVI Core. Okay, so we didn't try it. Maybe we didn't simply found it when we were researching this problem, so no.
Like also we needed something, as we said, that will share concepts between both. So, and this one seemed to be easy portable to the other platform. So we didn't want to end the situation that again we are doing things differently. Okay, so how it is done in TCA. So first of all asynchronous work is done through side effects. And then the state updates are done as responsive actions. And we have, because it's synchronous, we have a guarantee that during this update state won't change. And we have like we can produce a new state, and we have a guarantee that nothing will change in the meantime. So when we call like the readers function, call the action, it works on the UI thread, just gets the current state, mutates it, sends new one. So nothing will happen in meanwhile. Okay, so I guess it's really, I mean, this TCA has nothing to do with that. Basically, it's on your side, right? You can, what do you mean? Okay, so you received 409, I assume, right? Or you see that the state has changed, and then you can, again, make a new side effect for server to do something. But it's basically the logic part that you have to write. I mean, the TCA gives you tools, but won't handle this logic for you. Okay, so yeah, there's a really good question about how to integrate with like app extensions and stuff. So yeah, basically the store is a class or struct that handles all of those. And like anyone who has access to store can send it. But like app extensions usually run in their own processes. So I would assume that for this you will need to create like a smaller feature just for an extension that will eventually like write to the database or user defaults or whatever, so the app can see it or set notification for the app. So the store is like, okay, I'm taking this state. It doesn't define where the state comes from, right? The initial one. And how it is saved. Actually, point 3 now has a shared state implementation when you could just define, okay, this piece of state goes from my database. And potentially you could use it for this. So you say, okay, this state in the app extension like feature and my core app feature is the same. And it will do it for you. But it's like, you can have like multiple stores in your app. It doesn't say you have to have one. Actually, usually we have multiple stores.